Okay, you guys. Hyperbolic trigonometric trigonometric. Wow. Strike that. Reverse it. Let's try it again. Hyperbolic trigonometric functions. So we're going to compare how they're related. So first, circular versus hyperbolic trig functions. So most of the circular functions that we use are based on a point where the terminal side of an angle intersects the unit circle with the equation x squared plus y squared is equal to 1, right? That's why it's a unit circle. And you could do the same thing with any curve. So this applies to any curve. It'll still work the same way. And that's kind of what we're going to do. So here we have points x, y, where the terminal side of an angle intersects the right-hand branch of a hyperbola. So we're only looking at those that are right hand. We're going to treat it like it's centered on a unit, right? So our vertex is at 1, kind of like we set the unit circle to all be a distance of 1. And in which case we would use the equation x squared minus y squared is equal to 1. And we would have sine of theta, which would be equal to y, cos of theta, which would be equal to x, tan, which is y over x, right? So it's sine over cos. And then we have sech, and that would be the reverse of cos, or the reciprocal of cos, so it's 1 over x. And then we have cosec, which is the reciprocal of sine, so it's 1 over y. And then we have cothan, which is, instead of being sine over cos, it's actually cos over sine. Are these the proper ways to say that? Sure. They're standard. They're used regularly in hyperbolic trig as a standard, the naming I just used. But you can just think of it as sine h, cosine h, tan h, secant h, cosecant h, and cotangent h. A lot of people do, and that's fine. I don't think there's any, the name that I was giving really doesn't mean much. So again, sine of theta is the y value here, right? And cos of theta is the x value here, which would, be whatever it is. The sine value would be whatever it is. So they are related, and they do have a lot of the same properties. Let's look at how they look. So sine of x is a wave, and that's in this color, right? It's a wave function. Sine looks more like a tangent function in this case. Cosine, again, another wave, except for this time we don't go through the origin. And then cos is going to do that, right? So it's very much like one of the reciprocal ones. And then we have tangent. Tangent is our, right, it has reciprocals that go down, right? It doesn't cross. Well, than is more like a, what is that, cotangent? Or arctan? It's one of those. It kind of looks more like that to me. So some basic identities for hyperbolic trig. We know this one. Sine squared minus cos squared is equal to 1. This is the basis of hyperbolic functions. And interestingly enough, just like the Pythagorean identity for unit circles, we can derive the other 3 by dividing by, in the Pythagorean identity, where we have sine squared plus cosine squared is equal to 1. And we could divide each of these, right, to change them. This is really what we do when we change them. So you guys think there's more than one equation or more than one identity. They're all really the same identity. This would be 1 plus cosine over tangent. It would be cotangent squared, and that would be cosecant squared, right? And then if I divided this original function again by cosine squared, I would get the second one, the second identity. Same is true here. If I divide this by sine squared and divide this by sine squared, and this, I would get the other another identity, and I would do it again and again. So this is very Pythagorean, though it's not the Pythagorean theorem. It's very like it. So like the Pythagorean identities, we can derive the others by dividing by sine or by cosh. You choose. Derive the other 3 just for fun, the other 2 just for fun. I'm not going to do it here, but it does follow this idea. So we would have, let me see, so just what I did. Wait, do I have something else? Nope, I don't. Okay. I would have 1 minus cosh would be, cosh over sine would be cothan. So squared, and 1 over sine would be cosec squared. Right, so we derived 1. I'll let you derive the other by dividing by cosh in this original, right? We always take the original and divide by it. So those identities are there. What else is there? Is cosh an even function or an odd function, or neither? Is sine an even function or odd function, or neither? Explain and compare. Well, there's a few ways to look at this. They genuinely respond like trig functions. So what does it mean to be even, odd, or neither? Well, let's think. Maybe let's use sine, right? Let's just use sine. Sine of x. This is my base function, and we're going to consider sine of negative x. Well, this is the same as, or equal to, I guess this is equal to, oops, crap, equal to negative sine of x. So that makes this odd, right? If the negative input gives us the negative of the whole function, that's odd. And if we think about cosine of x, and we're going to consider that one, cosine of negative x, well, that is actually just equal to cosine of x, which makes that an even function. So we're explaining and comparing. So we could do, I think the first one they do is cosh, so of x. I'm going to compare that function. So what is cosh of negative x? Well, cosh of negative x is the same as cosh of x. So then that's an even function, which makes sense because we just saw that cosine is an even function. And then we can do the same thing with sine of x, so we'll compare that. Comparing that, we get that of negative x. Well, that's just equal to negative sine of x, which is indeed the same as sine, and that would be odd. So compare all of them. So compare the analogous and the similar trig functions. So you're going to do it for sine, cosine, tangent, cotangent, secant, and cosecant. And you're going to tell me which ones are even and which ones are odd, and compare them to the even odd versions of the other. This one should be pretty straightforward. I mean, you have to write some stuff up, but other than that, not bad. Now, this next one, you could do a few things. I guess I should mention that. How do you know that these are true? How do you know these are true? Are you just going to take my word for it? Because don't ever do that. Right? I make mistakes just like everyone else. I'm human. Stop thinking your teachers aren't. How do I show it? So let's consider another way to use cosine. What do we know cosh is? So not cosine, I'm sorry, cosh. So if f of x is equal to cosh of x, what's another way to write it? All your trig functions have other ways to write them. So that's just me putting stuff in and showing it. This here is me showing it. But that doesn't prove it. That doesn't justify it. That's just somebody telling me something and I'm going to obey what they say. I'm not doing that. So let's figure out how we can know it for ourselves. This is equal to e to the x plus e to the negative x over 2. Okay? That's another way to write it, using Euler notation. And you guys know there's Euler notation for all of this stuff, right? That's what I'm calling it. It does have a different name they like to use. What was that? Complex notation, which is fine. So now let's consider what if I do f of negative x. We know we want it to come out to be the same thing, right? Because we want this to show that it's even. But let's see what happens. So this is cosh of negative x. All right. So that means I'm going to replace x with negative x. So e to the negative x plus e to the negative x. Right, I only replace the x. Right, only replace the x. We say, okay, what happens? Over 2. Well, this becomes e to the negative x plus negative and negative becomes e to the x. Well, now if I reorganize this, we know we have associative properties, so I can group this and reorganize this here. So I'm going to do that, and I'm going to write it as e to the x, moving this piece here, plus this piece over there, e to the negative x over 2, which is the same as cosh to the x. So this shows that they are indeed even. And you go, well, okay, can we do this with sine and or shine? So we need to know how to write shine. So let me write shine in a different notation. And I'll let you guys figure it out. It's not too hard. Shine of x is equal to, and this is all in the book. You guys could read it. Let me make this big enough you guys can see it, because I do know this is e to the x minus e to the negative x. Still over 2, right? The whole thing is over 2. Making it worse. Awesome. That's an e. That just looks really bad now. Oh, wait. I'm going to erase that because that looks so bad. Oh, wait. There we go. I can do that. E x minus e negative x all over 2. Okay, that looks better. All right, so you guys can take shine and figure out if it's odd and see the relationship. You could compare all of them. Remember that cosh is 1 over secant, or secant is 1 over cosh, however you want to look at it. So they'll flip. Shine is 1 over cosec. Or sec is 1 over shine, however you want to look at it. And then remember that tangent is shine over cosine. So once you prove something about sine or cosine, you can use relationships of even and odd functions. So cosh or shine, you can use relations of even or odd functions. Part 3, use a calculator to make a table of values for cosh of theta and shine of theta. Where the values of theta are 0, plus or minus a half, plus and minus, a half, plus and minus 1, plus and minus 1/2, plus and minus 2, 2/2, and 3. So you're going to have 7 total cosines and 7 coshes and 7 total shines. And you're going to give a rough graph of these. You're going to plot them as ordered pairs. So you should have a total of 7 ordered pairs on your hyperbola. You can do this in any sort of software or calculator. You could do this in Desmos. Desmos is a good tool for this. And you can put in the table of values right there in Desmos, which is why I say that. All right, you guys, that's, I think, the last piece of this homework. So good to know you guys have done it. All right. I think that's everything. Have a good day.